Without further ado,
Okay, great. Thanks, Rob. So, just to introduce myself, I'm a computer engineer, worked in various startups, and then started various companies myself, many in the sort of connected product space, which is now sort of known as Internet of Things space. So the hats I'm wearing today are the second from last company I started. It's called AlertMe. It's a connected home platform. If any of you have seen British Gas's Hive product with the dancing elephants on TV, you can control your home heating from your smartphone wherever you are. That's AlertMe technology. And my most recent startup is called 1248. It's producing horizontal services for the Internet of Things. And hopefully by the end of this talk you'll understand what I mean by that. And both those companies have worked with a consortium called OpenIoT, which includes companies like ARM, on approaches to creating interoperability on the Internet of Things. So we see people in every single kind of industry connecting their products up. In health, all the way from the worried well to vertical medical applications. In industry, which includes things, not just things like gas pipelines and jet engines in the air, but also farms is an area where a lot of new sensors are being connected up and people are running their farms now on the data. In the smart city, the bits we see, like the buses and so on, the car parking spaces, and also the bits we don't see, like the sewers and so on. Hopefully we don't see. And of course, in the home. And the home's particularly challenging because it's a consumer market, the costs have to be really low, it has to be really simple, it has to be really reliable. So, an obvious question for a lecture like this is, what is the Internet of Things and how is it different from what has gone before? So I thought I'd just have a go at addressing that. And for me, this is the picture that really tells the story, which is there are about 7 billion humans on the planet right now, and best estimates are that that's going to level off at about 9 billion. But the number of connected machines on the planet is continuing to grow exponentially, and there's really no reason why that will stop anytime soon. So this is a very, very simple quantitative piece of evidence, but it leads to some quite interesting conclusions, because for every human, there are now more and more connected devices. And if we think back to the 1990s, we perhaps had one connected device, our PC. We had to spend a lot of time maintaining it, installing things, getting rid of viruses. You know, it took a lot of our time and attention. Now we've got mobile devices, smartphones and so on, and we probably have got several of those. We may also have things like Apple TV and Sonos and other connected devices. And because we've got more of them, we can't afford the same attention for each one. So they have to look after themselves a bit more, and they do. And so the Internet of Things, really, I think, is just the continuation of that trend. You know, we'll each have 10 connected devices, then 100, then 1,000. It might seem inconceivable now, but I think it's going to happen. And that shift will simply drive some great differences in how we interact with those devices, because we simply won't have the attention to give to each one. So, as well as Internet of Things, another buzzword that's around at the moment is big data. And that usually refers to the servers at the center of the cloud with very high velocity data flowing through them. And this is a visualization of Amazon's infrastructure. But the point here really is that increasingly the data that goes through those servers is not coming from humans, because there's only a certain number of us and we can't be sitting entering data all day. The data increasingly is coming from other machines, and increasingly machines at the edge of the internet, the sensors of the Internet of Things. And I think in time that data will overwhelm all the human-generated traffic. So really the Internet of Things and big data I see as just two ends of a spectrum, really. So has the Internet of Things happened yet? And if not, why not? What's stopping it? Well, I think the answer is vertical silos, and I'll explain what that means. So in any connected application, you have devices in the real world. There might be temperature sensors on the wall of this lecture theatre. And typically you then have a wireless connection often to some kind of gateway device, and the purpose of that gateway is to get those things online, to connect them to the internet. In the home, that gateway box would be plugged into your broadband and thereby connected to the internet. So then it connects to some kind of cloud service, which usually does at least two things. It stores the data and it does some sort of analytics on the data, so turning data into information that means something to humans. And then there'll be some kind of user experience, some kind of user interface, which often these days is delivered obviously on a smartphone. And of course, it's not just humans that are looking at this, it's other machines. So into that top API will be other services connecting, not just user interfaces. And the point is that in every vertical industry, whether it's measuring livestock on farms or temperatures in buildings or people's health in homes, you have exactly this same architecture. So at a high level, everyone's Internet of Things architecture looks like this. It doesn't matter what they're doing. You can always identify those same parts repeated again and again. And the problem is that everyone's doing it themselves. People are reinventing the wheel again and again. They're often using different standards when they do it. And really in these pictures, what matters isn't so much what's in those boxes, it's the lines between them. Those are the interfaces, the APIs, and the physical standards that connect devices to gateways and so on. And lack of commonality in the standards that people are using means that there is pretty much no interoperability between these different applications. So if you took a temperature sensor that was designed to measure temperature in buildings and you wanted to use it on a farm, for example, it wouldn't work because it would probably use a different physical standard for its wireless interface, and it would probably use different high-level standards as well. So this means that everyone's reinventing the wheel and there's no reuse or very little reuse, which means that everyone's having to do a lot of work to bring their solutions to market, which makes it slow and expensive. And that's really the obstacle. So everyone's stuck within their own vertical silos, and that's the thing we have to solve to bring about the Internet of Things. So if you look at the feature list of any early product in a market, you'll see a whole list of exciting features that you might want, and somewhere on that list will probably be words about openness, which means sort of compliance with some standards, ability to plug it into other things made by other manufacturers. But in an early market, and we're certainly in an early market when it comes to the Internet of Things, openness in practice is often at the bottom of the list. Because although it's a nice to have, in practice there's actually no one else to be open to, so it doesn't really matter. So if we take AlertMe 8 years ago when I founded it, we had every intention of making it as open as we possibly could. We chose all the open standards we could choose. We used lots of open source and so on. But the reality was that there was actually not very much else to be open to. There weren't other off-the-shelf devices that we could talk to. There weren't other cloud services that we could integrate with. And so, in reality, it wasn't very open. But as a product matures and as a market matures, you see that openness then rises to often being the #1 feature. So in the 1980s, I was working in a lab and we used Ethernet to connect our computers. It was 10-base-2 in those days, the old coax cable, but it did the same job as today's Ethernet. And when we bought Ethernet, we were buying it to connect our computers together. That's what it did, and we were happy. And then, of course, that market emerged and matured, and everyone started using the internet. And nowadays, when you see an Ethernet socket, you don't just expect that it's going to connect to the computer at the other end. You expect that it'll connect to the internet, to every computer. So the thing you're buying when you buy Ethernet is you're buying openness. And if it didn't do that, you wouldn't buy it. So as a market starts to mature, openness goes from being something that doesn't actually matter in practice to being the #1 reason why anyone would want to buy your product. And that's a very sort of important transition. So if we go back to this generic picture of an IoT architecture, remember we've got devices at the bottom, talking to a gateway, talking to cloud services, talking to some sort of user interface. But if we look at the kind of standards that are being used today, we see that certainly for the top parts of the architecture, it's all based on standard internet technologies, the web, standards like HTTP, RESTful APIs, JSON as a data format often. And so there is a fair degree of reuse and interoperability going on there. But as you get to the gateway, that all changes. And the internet stops at the gateway for almost all IoT applications today. And you then change gear into some totally different space, like Bluetooth or Zigbee. There are literally hundreds of different standards for doing that last hop to the edge device. And there's lots of good reasons for that. Often the devices are battery powered. The battery is very small. It has to last for a long time so that you're not having to constantly replace it. And the consequences of that are that the device is usually very bandwidth limited. In fact, the device will spend almost all of its time asleep. So 99.99% of the time, most IoT devices are asleep, saving battery power. And periodically, or when something changes, they'll wake up and receive, transmit. So, and each of these standards is designed for a particular use. So Bluetooth, a personal area network for communicating between things on your body. Zigbee is designed to mesh over buildings. Wireless HART is designed for industry. And as I say, there are hundreds of standards like this that are all designed for their own purposes. And they have in common the fact that they're not IP. They don't support Internet Protocol. And there is no standard way of translating between the Internet protocols and each of these standards. So everyone does it their own way, everyone does it differently, and the consequence of that is that every time you buy an IoT device, you also have to buy the gateway that makes it work. So if you contrast that to how Wi-Fi works in your home, you don't have to buy a new BT Home Hub or Wi-Fi access point every time you buy a new smartphone or printer or TV or whatever it is that uses Wi-Fi. They all use the one generic gateway because there's a standard way of translating between the internet and Wi-Fi. So a generic gateway can do the job. And that's not true today in the Internet of Things, and it's a major obstacle because it means that as customers buy more and more devices and more applications, they find that nothing works with anything else, and that's a huge inhibitor. So what's going to happen tomorrow? Well, I'll put, okay, let's start at the bottom of this picture. So down at the bottom, the standards that everyone uses today are not going to disappear overnight, but what is happening is that bit by bit people are making them IP capable. So now we can carry internet packets over the last hop. And there are a lot of consequences of that. So the really nice thing about the internet is that it's based on a stack model. So there's these OSI 7-layer stack. And up at the top, you've got applications, and down at the bottom, you've got the physical interface, which might be Ethernet or Wi-Fi or whatever it is. And the lovely thing about that stack model is that if you're an application, for example, you don't have to care how the data is getting from A to B. So, when your smartphone is picking up email, you don't know whether it's using cellular or Wi-Fi. In fact, the application, the email application itself doesn't know. And that's incredibly powerful because it means it can just think about email. It doesn't have to know about all the nasty things to do with communication. And so once we can carry IP everywhere, all the way to the edge, over any of these existing standards or indeed over some new standards, then we get that same incredibly powerful aspect, which is that we can write applications and build gateways without having to care what the physical standards are. So as we go up from the bottom, we've got a whole set of physical standards, but they'll now support IP. TCP and UDP are the two standards for carrying packets around on the internet. One is reliable and connection-oriented, the other is unreliable. You just send packets and they may or may not get there. TLS is the standard used on the web now for security. It replaced SSL. That's going to, the problem with IoT applications is that they're often not connection-oriented. And TLS requires a connection. So there's something called DTLS, which will come along and replace that. There's also a very interesting standard called COAP, which translates the very verbose world of HTTP, which is how our browsers talk to our servers today. And it basically translates that into something that's much, much more efficient in terms of bytes. So you can take an HTTP transaction that takes hundreds or thousands of bytes on the internet and turn it into a radio packet that has only tens of bytes. So it can go over these very slow, power-efficient networks that are used right at the edge. And do so transparently. So it's translating transparently. So in the cloud, on the web, people think they're talking to a full-blown internet-enabled device, and they don't know it's actually being translated into this much more compact format. The other thing COAP deals with is that most of these devices are asleep most of the time. And today's internet protocols cannot cope with that. So on the internet today, if you talk to someone else over the internet, you expect a reply. And if you don't get one, you assume that it's broken. Whereas on the Internet of Things, you won't get a reply most of the time because the thing's asleep. That doesn't mean it's broken, it just means it's asleep. That's how the IoT works. So CoAP deals with that. So it can basically store messages and then forward them to the device when it next wakes up. And it can also register interest in changing values. So when the device wakes up and the temperature changes, for example, then anyone who's registered an interest will get a message back saying that the thing's changed. Up in the cloud, the same standards as today will be used, HTTP, REST, JSON, and so on. But we need something above those because today, if you have a client application talking to a service, say the client application knows about temperatures. It knows how to plot temperatures on a chart. Say the service has some temperature data in it from a sensor. At the moment, there is no standard way for the application to find out that the service has got temperatures in it and to understand them when it does. You know, the temperatures might be called temp or temperature, they might be held in degrees centigrade or Fahrenheit. Until you've got some commonality between the application and the service, then they can't talk to each other. There's a problem with semantics. So the magic words there are semantics, ontologies, taxonomies. Until you've got some kind of compatibility up at that high level, you can't make stuff just work. It requires humans to come in and write code to glue everything together. And the problem with that is that humans don't scale. There aren't enough humans to be writing code all the time and gluing things together. We need machines to be able to sort things out for themselves. So there's a lot of work going on that. MQTT, AMQP, there are a number of streaming protocols. So today's web is very much request response. That's not very efficient for the Internet of Things. What you typically want is to say, well, just whenever the temperature changes, just tell me. I just want you to stream temperature changes to me and do so efficiently. And so these standards like MQTT and AMQP handle that. And then IPSO profiles. So again, to make an application and a service compatible, they need to share not only low-level concepts like how do I represent temperature, but also high-level concepts like what is a thermostat or what is a smart meter. You know, on a thermostat, what parameters do I expect? There'll be a set temperature, a temperature I can read, and so on. And at the moment, profiles for devices like that are built into the standards like Zigbee and Bluetooth. But because they're built into those standards, you can't use the profile unless you use the whole standard. And the problem with them is that none of them are compatible with each other. So various people are working on defining profiles which are totally independent of all the lower layers, so that when you have a thermostat, everyone will agree what a thermostat is, and it doesn't matter how it works, it doesn't matter what low-level standards it uses. And of course, the background to all of this as well is IPv6. There's a big IPv6 transition happening right now. I think about 3% of the world's traffic is IPv6 right now. It's growing about 50% a year. It will be largely invisible to normal people. There are mechanisms in place to allow you to translate between the two worlds seamlessly. The key thing, obviously, about IPv6 is it allows a lot more addresses. And with the Internet of Things, you know, we'll need all of that address space. So I just briefly wanted to touch on something called Hypercat that I've been involved in. It's an early stage initiative, but it's representative of some of the things that are going on in the space. So it's something a number of companies have been working on over the last year. And it's essentially trying to work on this problem of how an application can discover data that it understands on a service. So Hypercat doesn't actually define the ontologies, it doesn't actually define how to represent temperature. It simply is a standard way of exposing stuff which you may or may not understand. So it's a sort of sandpit in which you can then discover whether you're compatible or not. So if we think forwards 10 years to 10 years' time, there'll be a lot more connected devices. How will we think about the Internet of Things? And my prediction is that we won't call it the Internet of Things anymore. We'll just call it the Internet. So very briefly, I talked about the most recent company I've formed and the fact that it's working on these horizontal slices. So functionality that's applicable no matter what vertical industry we're trying to build an application for. We're basically in the business of selling our know-how, but also encapsulating that know-how into services that people can buy off the shelf. And the first offering we've developed is a time series database. So something that everyone wants to do in every IoT application is store the data. And typically you've got a lot of devices trickling data in, for example, temperature readings every minute or two. And if you imagine you've got that kind of data flowing in for a couple of years, and now the application wants to ask a simple question like, is it hotter this year than last year? That could require you to do millions or even billions of calculations, and you want the answer right now. So adapting those two worlds to each other is one of the jobs of a time series database like Jerris. So that's all from me. I just wanted to mention, if anyone's interested, 1248 has some summer internships available, and if people would like to talk to me about them, then that's my email address. Thanks very much.